talk about diagrams. And these always comes as some extra complication because like there's a law that if you want to work on this field, you have to come up with your own notation for the diagrams. So I'm going to try to explain two different kinds of notation and what's the advantage of each one of those two notations. So there is what I call style 1, in which, as I said, we only have one kind of vertex in EFT of LSS, which is this triple vertex, right? So the idea is the following then. We have two different time slices, the final time, and the initial time. And we want to connect those time slices. And the idea is that you have some propagator that brings you from TI to TF, and this, like a linear line here, connecting the 2 points is what we call delta 1. So this is just the simple propagator that brings you from TI to TF. And in this case, delta 2, which is the second order guy, would be something like this, in which here you have either alpha or beta the vertex. Oh, thank you. I still want it.
Still want it.
Okay. So I'm going to try to draw linear lines as dashed lines and nonlinear lines as solid lines. So as you see here, we have two delta 1s here downstairs that interact with a vertex alpha or beta, giving rise to a delta 2. So they propagate, and this interaction here happens. So the time dependence can be understood as something that happens in between TI and TF. So the interaction, the moment of the interaction between those two modes that are P1 and P2 can happen in between TI and TF. So for delta 3, again, you have something like this, but now you have 3 different legs. And as you can see, in this notation, I always keep triple vertexes here and here. So delta 3 is generated by one triple vertex here and one triple vertex here, right? So in this notation, which I call style 1, you have the diagrams that basically summarize the two one-loop contributions. So for instance, P22, how do we read the P22 is basically connecting this guy with a symmetric guy, like another guy like this one, which means you have something like this. So the contraction we take is always connecting two different legs in the initial time slice. So you connect always, so imagine you have, okay, so this would be one of the lines, and you connect always 2 lines here downstairs. So you would take contractions like this one. Not exactly this one, of course, but similar, right? And then the contraction would come like something like a cross or something like this. And the way to read it is there is an interaction here, R alpha or beta, an alpha or beta here, and here each one of the cross, which is a contraction, is a P11, right? So this is one of the ways to read it. Yeah, so for P22, you take basically this, and then you connect this and this. So as you can see, if you connect those 2 lines here, if you connect 2 of those lines here, you get something like this diagram, right? Each one of the contractions here is a power spectrum. So, okay. And here is K, I, and here's K. K1 and K2. And you have, of course, K1 equal to K2, because you have this direct delta in the beginning, right? So why do you care about the P11 here? Right, because then you can write down, all the loops we construct are on top of delta 1s, right? So always the propagator is P11. Yeah, so you know the number of P11s are 2 here. I'm going to briefly close this. So here you have 2 P11s, And if you have momenta p here, you're going to have k1 minus p, right? So this tells you that this diagram should read as something like integral of p11 of p, p11 of k1 minus p, and then you have something like an f2 here, right? Okay.
So where are the alphas and betas in this?
So this depends on the fields you have here and here, right? But this would be basically alpha or beta here, alpha or beta here. But if you have delta, delta, you can have, so this has to be a sum of two contributions. Because if you have delta going to delta, you can either have, so the two vertices as, so we normally have beta, sorry. So beta is the vertex that we have for theta, sorry, theta, theta going to theta, and delta is the vertex that we have for delta theta, right? So you basically have something like, if you have delta and delta here, you have a theta, and a delta, and delta, right? So this would be an alpha, basically.
So you never have a delta, delta, delta vertex. There is no delta.
No, there is no delta, delta, delta. Yeah, it's actually a linear combination, sorry, because, yeah, to be clear, in the first equation we have something like delta 1 plus theta 1 equals something like delta theta alpha, right? So this vertex basically generates a linear combination of both. So you have basically all kinds of combinations of them, right? So alpha is the vertex that comes with alpha and theta, alpha, delta and theta, and here you have a sum of delta plus theta, right? So it's actually something more complicated. But yeah, I don't like the way of thinking like this. I think it's better just to think as alpha. So this we can think about this guy as F2 directly. It's easier, right? Okay. So this is one way to think about it. And the other diagram that we would have is something like connecting a 1-tree diagram. So you can connect this guy to basically one of those legs. So this means you have something like connected to something like this. Right? So this would be the P1 tree. And in this notation, it's pretty clear that all the interactions you have are always cubic. Okay? And this diagram, I mean, if you just linearize this diagram, it would look as something like, just make it like in the same line, it will look as something like this, right? Okay? Just the same diagram. But so if you want to draw directly the connections like the P1 tree, you see that, so the reason why this notation is slightly more complicated is because you cannot see directly the F3 kernels here. I mean, they're hidden, basically. F3 is the sum of those two kernels here, right? Because F3 is given by the interaction between delta 1 and of this delta 2 that comes out. So this is a delta 2 that you have in the middle that interacts with another delta 1 and sources a delta 3.
Sorry, dash lines, they're always delta 1, and the solid lines, or what?
So solid lines are nonlinear deltas.
Can be delta 2 or delta 3?
Yeah, doesn't matter. I mean, it's my notation, so I decide how to draw those lines. But something we can see here is that the loops start exactly by connecting linear legs, right? And this is something that normally comes as a question, what are those loops for? So what we are taking here as the loops are basically, you're integrating over different initial conditions of the universe. You're interacting over, so the loops comes from these contractions which basically correlate different initial points, initial fields of the sky. So this means you're averaging over different initial conditions of the universe. So the loops that appear here are not quantum loops in the sense that we don't have like off-shell particles propagating. It's just different realizations of our universe, because delta 1 of k, the vector k, actually has some variance on top of it, right? So this is an stochastic field, which depending on the initial condition, you have to basically, when you cross-correlate with another delta 1, you have to basically take all the possible initial conditions into account, right? So the integrals that we have are just a consequence of the different possible initial conditions for your delta 1 field. Cool?
So I think you mentioned that, but this P13, for instance, right? The solid line is 3, delta 3.
So here you have,
Solid line is delta 3.
this one is delta 3, yeah. And this one,
Delta 1 and delta 1.
yeah.
Then the vertex delta 2, delta 1, delta 1 is what you said. It's not really a vertex. It's something that's contracting from delta 2, delta 1, delta 1.
Yeah, this is the delta 2 here.
Oh, so now you're having a rotation where the dashed line.
Sorry. Sorry, you're right. As I said, I choose my notation. it's a floating notation. Okay. But, okay, there are some advantages of this notation and some also disadvantages, because I think you cannot read directly. So here you can connect directly to alpha or beta, right, as I said. So those two are either alpha or beta. But you cannot read the F kernels as, I mean, for F2 it works because the F2 is quite simple. But for F3, you cannot read directly the F kernels, as I'm going to make clear in the next notation. So the advantage here is that there is a line you can draw, there's an arrow you can draw, and this is the time direction, right? And you can think about the time propagating in this direction, and you can think about the interactions happening at every single point. So actually there is an integral here in time for which you have to consider that the interactions between those two delta 1 modes can happen at any time between T initial and T final.
Okay, I'm confused again, because usually when you say correlation functions,
Yeah.
these are same time correlation.
Yeah, I'm thinking about correlations at the same TF final time slice.
Okay.
So I'm fixing the time slice, the final time slice should be at TF.
But then the delta 1s are in a different time.
Yeah, the delta 1s here are T initial, and here is T final.
Right. So you must have vertex in this transit. So this delta, for instance, in the loop, you have this delta 1s propagating. I don't know what to call it.
Yeah, delta 1s here.
But this delta 1 is delta 1 at T initial.
Yeah, exactly. And so those are delta 1s at T initial. But, oh yeah, okay. I'm going to come to this point, which is the interesting thing, which is for Einstein de Sitter, time factors out, right? So what we can think about generally, beyond Einstein de Sitter, we can think about this mode propagating between Ti and Tf. And what you have here is D, right? Yeah, the growth factor you have here. So it's the same, right? You have between T, you have a D here. So this is, let's say, dTi, Tf. But this is in between Ti and something T, let's call intermediate, because this is going to propagate in between here and here. And that's why in beyond Einstein de Sitter, like you have some corrections, because this interaction can happen because like at any point in between Ti and Tf. But when we consider Einstein de Sitter, time factors out. So we know, so what you're saying is that D times D, so you have two factors D, this D and this D. So you're going to have two Ds, D squared. Like, let's say, or something like this plus this, right? I have to think. But anyway, you say that basically these processes of this evolution, and this evolution basically leads to one single D from Ti to Tf. So that's the assumption. That's the Einstein de Sitter assumption. So when we basically remove those Ds, we factor out the Ds, what we are saying is that, okay, you don't have to integrate in time. Because normally, if you do the full calculation, if like, you can check, for instance, Croce, Scocimaro. So the expression they write down, it's in this matrix formalism, and they have the integral. The integral for this interaction, they show that can, like, they have a full expression for this, in which the interactions can happen in between any time in Ti and Tf. So in the end of the day, what you say is that if in Einstein de Sitter, these integral factors out, and everything is quite simple. So we go to answer this here in which we don't have this, and we can say basically time decouple such that we only have the space direction. But these formulas makes quite clear what's the time directions of the arrows. And if you want to draw some arrows here, you have to go from the initial slice, which is this direction, to this final direction here, right? I'm not drawing lines, I mean, I'm not drawing arrows, but if you want. Yeah. Yeah. Yeah, exactly.
That means that if somehow you expand that cross there, you have that, like, yeah, is in there encompass like somehow the. Could you expand that and draw the P11 diagram there? Because I don't see the really the mapping.
So this.
There you would be drawing in the P22, you would just take the 2 times the like 1, 1, 2, 2.
Yeah. P1, I mean, the cross here is just a notation. I could have a, so it's just this contraction you get here.
But what I'm saying, it's just a line, or is it 2 lines from delta 1?
It's 2 lines, one line coming from this direction and one line coming from this direction that contract at this point, that collapse at this point. So whenever I take a contraction, which is what I take like when I calculate P22, these guys are gonna appear, right? I just took like, for instance, the F22 is something like F2, delta 1, F2, sorry, F2, I'm using this notation. So I'm just collapsing and taking the contraction between those fields here. And this is what I'm writing as a cross here. Okay? Right, so the advantage of this notation is that the time direction is clear. And if you think about something beyond in the series, you can think about the time direction as flowing from this direction to this direction. And another advantage is that it keeps the triple vertices, right? Manifest, it's manifest there. But something I call style 2, which is the one I use most, is forget about this story about like propagating lines, because as I said in 19 this year, we know time factors out, and we can always approximate, like go try into the seeder and then go back choosing the right growth factor, such that we write P22 instead of as something like this. So this would be K1, and this would be K2. And if you write P22, you always come with 2 lines going out. So this would be directly the F2 kernel. And then you take the contraction here. So for P22, it's actually the same. Okay, it's similar. But for P13, then you do the same. You take the squares here. But for the F3 kernel, sorry, let me keep the notation consistent. And here is F1. I have only one line that then goes here, and then another line that goes here. And this is slightly different than this diagram, right? This is something that goes as a blob here. So you see that the vertex here has 4 lines associated to this vertex. But it's fine, because I always think as this, like this as an external line, this as an external line, and the lines that goes out of this interacting vertex here is basically different delta 1s. So I just let the F1s go directly out of the vertex. Yeah, exactly. This makes clear that this is an F3, and this makes clear that this is an F1. I prefer this notation more, but this notation makes clear something physical, which is the triple vertex and the time direction.
So there, what was the edge that was representing delta 2 in the other case? So can you, in the P13 of the time case, you have the vertex, like the line connecting the two non-linear explicitly written. Is there somehow excluding the F2? It's the F3 box.
Yeah, this is the F3 box, and this is the F1 box. And F3 box, this you consider as a box. And inside this, you basically, what you're doing here with this F3 is to take this vertex here and bring down to T initial, right? So you're basically collapsing this line, okay? It's just a notation. And it makes clear, it doesn't matter. Like what you're saying is that you don't care when this interacts with this and this interacts with this second mode. You're just saying like, ice and the Cedar factor is out such that they interact basically at the initial slice and everything goes as the linear growth factor, okay?
The right line to the dash.
This one here? Yeah, yeah. 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 Okay. But, I mean, as more papers you read on this topic, like you're gonna notice each one of us come with a different notation, so it should be something flexible. Yeah. But yeah, long story short, there are those two kind of vertices you're gonna find. No, the Fourier convention is always the same one, always the. So the advantage of this is that it's cleaner. I think at least. Yeah, of course, for me, this is cleaner than, I don't know. This looks very similar to these other, I don't know. I got used to this one. And, right, and there is a direct connection. To the F and the G kernels. So you basically bypass alphas and betas. I think this one is mostly used. Right, but as I said, in equations of motion, right, so I'm going to repeat myself, but now I'm going to write the equations with a lambda, because, as I said, the problem is now is that whenever you compute those loops, you find so you find, as I said in the first lecture, that basically depends on the cutoff you choose for the integrals, right? So whenever you compute those loops, they're going to depend on the lambda you put here. So there's a lambda dependence here. That for the one loop in the left, yeah, it's mild, but it's there. For the two loop in the middle, it's there, and for the three loop, it's huge, right? So you find a strong lambda dependence that you have to account for. So it means we have to basically write down equations that are directly lambda dependent. So the fact that it depends on lambda is not only like the problems, because as I said, you have also this convergence issue. Does it converge? Does the series converge? And what we see is that when we take the highest cutoff, like take lambda and bring close to infinity, we find that for lambda CDM, the three loop contribution is larger than the one loop contribution. So this means, as I said, that the Taylor term, basically the third Taylor term, is bigger than the second one, which is bigger than the first one. So there's something sick there, right? So this has to do with the cutoff. Yeah, the integrals converge, but this is the point I'm making on the right plot. So on the right plot, I'm showing that they converge, but I don't care if they converge. They're converging to the wrong result. So as you see on the left, so this is a one-dimensional problem. They took the one-dimensional problem, for which you can go to 20 loop order in SPTs. So you see, it converts. So when you compare, the blue one, which is the 10th order, to the purple one, which is the 20th order, it converts, right? But when you compare to the simulations, which is the dashed blue, actually you're finding it converts to the wrong result. So it's not moving directly to the simulation result. So even if it converts, the question, if it converts to the right result, is a different question, right? Yeah, the integrals converge. So it converts, and the fact that it converts first is a matter of luck. It's a matter of the cosmology. It turns out that we live in lambda CDM for which those integrals converge. For which, because the convergence of those integrals you have here depend on the p's you choose. Depends on how this p, the UV limit of the linear power spectrum. It turns out that for lambda CDM, it converges, but it could be different, right? So actually, the fluid description like should not, I mean, we understand there's something wrong, there's something beyond this that should account for this correction. So the second point is that it converges to the wrong result in the case of lambda CDM. As you show here for the 1D case, okay, it's 1D, but when you compare the dashed blue to the 20th loop order like here, you're seeing that it's not moving towards the right result, right?
That means what? You're forgetting something?
Yeah, it means we are forgetting something. It means that it doesn't matter, bring lambda to infinity, you're not getting the right result. So this perturbation theory is not converging because you don't have the, it's converging to the wrong, or not converging, or converging to the wrong result because you don't have the right description, you don't have the right fluid description. There's something missing in the fluid description, and we know what's missing because in order to draw all those diagrams here, we're actually dropping one important point in the Euler's equation, which is sigma ij. So we're basically considering a perfect fluid, and we know the universe doesn't behave as a perfect fluid on small scale. So,
that plot, you're taking lambda to infinity.
yeah.
One of the assumptions also that was to perform at some point was the fact that we're extrapolating the TS splitting in time and space also to the case of lambda CDM.
Yeah, but this is not a problem because this is a percent point, sub-percent point. You can show that.
You would do the same thing on EDS universe?
Doesn't matter, doesn't affect. Same issue, same issue. EDS is not the problem. Going like to the EDS approximation is not one of the issues. You can show it's below 1%, and you cannot explain a 1% difference between those two lines, right? So the whole point is that the fact that there's something like intrinsic here. What we are saying when we bring lambda to infinity, we are saying that you can take the modes here, that you trust this alpha and beta interaction that you have here between two modes, delta 1 and delta 1, down to very, very small scale, right? You're saying that this interaction can happen at any scale, and I trust this alpha and beta vertex. But there is no physics, no new physics in the UV that are going to fix this alpha and beta. So when you say, when you take lambda and bring to infinity and say, I don't need anything else, and this fluid prescription is right, down to a very small scale, what you're saying is that I trust that I know how those two modes interact, how P1 and P2 interact, even if this P is the scale, I don't know, of at the length scale of us, right? This is what you're saying when you bring lambda to infinity. You're for the simulation?
Yeah.
For the simulation, the story, it's a different story, right? Because you're not solving directly the fluid equations. Right, so what's the new physics? What I mean is, so we know dark matter is collisionless, right? In the case of simulations, of dark matter simulations. So we know inside this prescription, there is not something that tells you, like we have considered a perfect fluid approximation. We did not account for velocity dispersions into this prescription. Right? There's something missing in this prescription, which is telling you, okay, suppose let's take length scales. So if my P1 and P2 live here, and I know like nonlinear scales are here, I trust more or less how those two modes interact, right? I trust my prescription is fine, perfect, like the perfect pressureless, perfect fluid approximation holds here. But we know it doesn't hold here. So whenever I have interaction of a mode that lives here, of two modes that live here, or one mode that lives here with another one that lives here, the fact that it happens where I don't trust PPF, the perfect pressureless fluid, means like there is an interaction here which I'm modeling in the wrong way. The coupling here cannot be alpha and beta. It has to be something else that I don't know. Okay?
This is happening because of the contraction that you're doing for the nonlinearity,
So
so to speak. Because you're saying that I trust this perfect fluid approximation on the left, which would be like I trust how I'm propagating delta 1 in Ti to delta in Tf.
no, this is not the problem here. The problem is here. So the problem is for which modes I trust this interaction. So the interaction between two different modes. The interaction, I mean, doesn't matter when it happens in time. I mean, the time is not a point. The point here. Exactly. So if I want to go beyond the perfect fluid approximation, I have to change and come up with something else. I mean, or you come up with something we call a UV completion that tells you what's the new dynamics that happen here. And this can be like, for instance, as I think it was Francisco that asked me like, what happens if you take like the phase space distribution and assume a phase space distribution. This comes as a UV completion. You're saying, you're given a partition function and you're saying, what's this partition function? And basically, it can be either this, and this was attempted in this paper, for instance, this VPT scheme that I mentioned before.
It's a non-equilibrium distribution.
Yeah, it's a different, you choose a distribution function.
That's not an equilibrium.
Yeah, that's not an equilibrium because you still have, yeah, it's basically changing. You assume a distribution function here.
F beta is 0.
So the collisionless part they keep.
Yeah.
The point is that they account for the whole Boltzmann hierarchy, right? So this is the difference. It is still collisionless. I think in this VPT case, it's still collisionless, but they account for sigma ij, so they solve the Boltzmann hierarchy. Way more complicated, of course.
Refer to paraphrasing case, this means this is correct. So what you're saying somehow is that if you go to sufficiently nonlinear scale, meaning you have had like shell crossing,
Yeah.
you will have some kind of velocity dispersion,
Yeah.
which is the thing that breaks the perfect fluid approximation.
Exactly. Perfect. 100% true.
You think that you don't have a way to model that if you don't have a
You can either choose to model sigma ij. So there are many options. So you can either choose to model sigma ij and just say, I trust, I know my UV, I know how particles interact on small scale. This is one choice you have. The choice I'm going to take is not to model sigma ij and just say, what's the most general sigma ij I can have? It's a different choice. In one, I'm being very conservative and saying, I don't know anything about the small scale. In the other one, I'm saying, I know the small scales. I know how they interact. I know 100% the small scales. And I want to understand what's the, I mean, it's just different choices, right? So in the end, when we run simulations, what we do is like, okay. Sorry? Well, in the simulation case, we assume a phase space distribution, right? But what we don't know, I mean, the problem now is the resolution of the simulation. So it's a different matter. It's a different problem because in the case of simulations, we have like a space grid, a smoothing scale on basically the partition, the distribution function f directly, right? And this generates a problem, I mean, which is aliasing, so just.
let's say, run an n-body simulation without smoothing, which is not correct physically, but you can do that operationally. And then you would be able to write a partition function for that. You would be able to employ that in deformalism and have a converged result.
So the point is, if you can solve those equations as well, right? Because probably the sigma j you're going to get is rather complicated. So this, I mean, you can always plug the simulation ansatz here. Whether you can solve these or not, I mean, it's.
So that's why basically here you go to Seldovich, which would be something like you're going to the nonlinear.
So.
Seems to be converging to the black.
Right. So, okay, so this is another thing. Yeah, so this is a nice thing you pointed out. So in 1D, the full Euler perturbation theory basically converges to Zeldovich. And this is what I'm pointing at, like they point out here. And you can show this analytically, that if you take infinity loops in Eulerian space, it converts basically to Zeldovich. So that's why they say it's infinity order here. Yeah, yeah. It's basically some resummation that happens in 1D. Okay? So there are 3 different problems. First, the lambda dependence that is there. The second is the series convergence, which, as I'm showing here, doesn't converge. At least like when you go to higher and higher loops, it doesn't converge for lambda CDM, here in this case. And the other one is the question, even if it converges like numerically to a finite value here, as it does here, it doesn't converge to the right result. And everything boils down to the same reason. And the reason is that we don't trust the fluid prescription that we have down to very small scales. Okay. Very ambitious title, of course, but so this was first noticed by those people and the fact that we can write down the same equations we had before, but now for smoothed fields. So now we have exactly the same equations. But now we have everything that we had, fields that you knew before for all the modes. Now you're basically truncating the modes and saying, I trust my theory up to some lambda scale. I'm just smoothing out the equations such that now everything here is moved such I'm truncating everything in one scale lambda. And as I said, this lambda, when I take the scales of the problem, I always take my case LSS for which I'm interested in, and this lambda has to be smaller than something like K and L. So you want some hierarchy of scales in which lambda, the cutoff you take, is larger than the scales you're interested in, but also the K and L, the nonlinear scales, are also larger than lambda. And the way to estimate this scale here, the scale in which perturbation theory breaks down, it's just an estimate because in practice, the scale in which shell crossing happen and you generate velocity dispersions is basically something you have to find a posteriori after, for instance, running simulations or something like this. But we can estimate this scale should be the scale for which sigma square at a scale K and L is order 1, in which sigma is the variance of delta 1. So if you take delta 1 here, it's the variance of the linear density field. And this, of course, as you smooth delta on different scales, basically this sigma changes. So it's the variance of the linear density field, sigma square, let's say on a scale R, like is equal to integral of P. Okay. Okay. There's a square here, but. Okay? So this means that whenever the variance of the field here becomes order 1, so whenever this guy becomes order 1, which means the variance of the linear density field, you cannot trust that delta 1 square is smaller than delta 1, right? So this is something we want for PT to be valid. So in this type of diagrams we had here, we can decompose on two different things. So those are the interactions we trust. Now everything that's below lambda we trust. And everything that's larger than lambda, every interaction of modes, let me draw with two different colors. So everything that happens, if there are some modes that let's call delta UV1 that interact with something that's delta 1 lambda, what happens here is not something like alpha and beta, but it's something you don't know, okay? And similarly for two modes that are UV. Yeah. Right, so the window function you choose, of course you want, so in the end, as long as you keep this hierarchy valid here, the window function shouldn't matter much, right? As long as, of course, everything here is going to be absorbed by counter terms in the end. Yeah.
So you're saying that your cutoff scale could be smaller than 2.3?
So at Redshift 1, I don't think it's 3. It's something like 0.8.
No, yes. And Redshift 0 is around
0.3. Yeah.
So your lambda, where you're containing the integral is below 0.3.
This depends on Z, of course. Yeah.
Very large scale.
So
For the lambda.
for Redshift 0, this guy here is around 0.3.
Yeah.
Yeah.
So you cannot push it with the FT of lambda S to 0.3.
Yeah, in Redshift 0, forget about it.
So lambda depends on redshift.
Yeah, lambda depends on Redshift. And K now depends on Redshift, right?
In the case of lambda in the end, will try to make it disappear, right?
Yeah.
When we renormalize it, then you have no explicit dependence on lambda.
Yeah, exactly. And in the end, okay, what I'm going to say is a bit, okay, you have to think a bit about this, but when you take lambda, the fact, this is something you want, right? But in practice, if you take lambda to evaluate those integrals, when you add the counter terms, as I'm going to explain, and if you take lambda to be infinite here, it also doesn't matter. The fact that lambda is larger than k now means, okay, everything that's perturbative is embraced by perturbation theory, which is here, and the fact that lambda is either here or here doesn't matter as long as I add the proper counter terms. In practice, it's just as a matter of evaluation. If the integrals are independent, like you can show that the integrals depend. If you evaluate lambda here or here, the results are going to be different, as I said. But if you show that if the integrals plus the counter terms at this scale are exactly the same as here, in practice it doesn't matter. So that's why in practice we take lambda to be large and we don't care about it.
So I think lambda is having two roles. One is regulator of the integral.
Right.
One is saying when the sigma j is important.
Right. So lambda here has two different. Yeah, I'm gonna come to this. Yeah. But okay, the first thing here is to understand that we don't understand exactly the interaction between those two modes, and the interactions between one large scale and one small scale mode is what's going to be parameterized by something new, something which is not alpha or beta, but let's draw something generic here, which is a new counter term. And the interaction between two modes, two UV modes, is something that we call also stochasticity. So the way two small scale modes interact is something we don't actually understand. And this is something we call like, because this is a UV mode interacting with another UV mode. So, okay, let me follow my notes, otherwise I'm gonna get trapped on this. But the idea, the long story short idea is the following. We want to draw some delta n's of k that are lambda independent, which are the smoothed version of lambda plus some counter terms that depend on lambda. How to find those counter terms? So what's the shape? How does those guys look like? So this is the question we have to find now. And the question we have to find now relates to what Rogerio mentioned. So let's regularize the integrals we had before. So let's go back to the integrals we had here and ask ourselves, how does those integrals here depend on lambda? Such that all lambda dependence here can be absorbed by some extra terms. So before mentioning how to regularize those integrals, let me mention one important property of those F kernels. So generically, when you have an Fn kernel and you have arguments like P minus P, and the sum, let's call K, as the sum of all those arguments here of those functionals, whenever you have P way larger than K, so this is a property of those kernels. You can check the property of those kernels. This comes directly from the fact that you can expand those Fs in terms of P over Ks and the properties of the alpha and beta kernels. So this boils down directly to the properties of the alpha and beta kernels. We know that F n's are going to be proportional to K squared over P squared when K is smaller than P. Then you're screwed. I mean, you can always think, you don't have, it's a not very pathological thing, right? You can always think about what happens at k.5 in Redshift 0. And the answer is try to find another framework, because this one is not going to work. So you could see anything. You could see anything. You don't have control of what's going to happen. Probably you're going to see some series divergent. You're going to see some divergence. And just because, again, the loops, even after adding counter terms, would not, as I was showing here in this plot, when you add counter terms, you find that the hierarchy between the terms is restored, right? After adding the counter terms and you don't find this, it means it's still pathological. So it means you don't trust the perturbative regime anymore. Right. So what you're mentioning is that here we're crossing, and here you would claim like I don't. No, it's rather simple what's happening here, because what I'm adding to this plot, to make this plot, what I'm adding are just the leading counter terms. I'm not adding the full counter terms. So this means I'm just adding the first counter terms you would have to add to show that they fix the large scales. Because the first counter terms are exactly those ones that fix the larger scales. And then as you add more and more counter terms, they would restore and improve better and better on small scales. So I'm just adding the first counter term. Exactly. You fix basically scale by scale, right? The first counter terms you add, fix, restore those scales. Because the counter terms are basically also power counting in K. So the counter terms are basically K squared, K to the 4th, K to the 6th. So you can find them as basically first restoring this K, and then restoring this K, and then restoring. Oh, below the. Well, you can always compute the next two leading order counter. I mean, it's feasible. We did. It's just that for this plot, we're just adding. So the point is that it's a lot of counter terms you add, and it's quite hard to disentangle because the same counter term that contributes to one loop contributes to 2 loops and 3 loops. So it's quite hard to separate the piece that's contributing to each loop. It becomes basically messier. You cannot say this counter term is exactly like it. It's when you fit everything together, basically with the power spectrum only, everything kind of mixes. But the point is that here it's going to be fixed. Like the large scales we can isolate clearly. Make sense? Yeah. Oh yeah, definitely. The same counter term that adds to the power spectrum adds to the bispectrum.
In that case, you will see some rank ordering breaking in the same kind of scale.
So the power expansion for the bispectrum is different because the bispectrum has an extra leg, right? So the leading order bispectrum is basically the same as the 3-level bispectrum is basically the 1-loop power spectrum.
What if in theory for each operator you have a counter term which cancels the version?
Yeah.
But then the form of the counter term depends on what order perturbation theory you're going, right? So
Yeah.
I would claim that CT of lambda there should depend on n as well.
Oh yeah, definitely. It depends on that. Yeah, you're right. Okay. So this is just a property of those F kernels. And one thing we notice about those F kernels is that, okay, now we know the UV limit of those F kernels. So it means that when I compute P22, which is something like an integral of P, K minus P, P of P, F2 of K minus P, P, right? I know that when I take P to be larger than K, I write it down as something like P square of P, sorry, there's a square here, missing. So F goes as K square, P square. So I have a K to the 4th over P to the 4th. So this is just K to the 4th times a number. Okay? So this means that if I want to fix the lambda dependence of this guy, when I take P and bring it to infinity, the guy I have to add to fix the lambda dependence has to be a number times K squared, K to the 4th, sorry. So it means that P22 that doesn't depend on lambda is basically P22 of lambda plus a number times K to the 4th. Okay? So this guy is lambda independent, this guy is lambda dependent, and this guy cancels this lambda dependence. Yeah, yeah, I'm bringing lambda to infinity. And what do we call this number is? Yeah, there's a finite part that's left.
Then how do you determine the finite part?
But the finite part is fine. The finite part is physical.
So it's not ambiguous.
So it's everything that's ambiguous is absorbed by this part. The finite part, the part you trust, which is the part in which lambda is smaller than k now, is kept in the theory. This is calculated. This is there. And then you can cross-check that which lambda you take here, basically, if you add counter terms, it basically cancels out compared to another lambda prime you take close to infinity. Okay? Right, so this number that's here has two different functions, as Roger mentioned. first to regularize the theory, basically canceling out any lambda dependence that remains here. The second thing that it does is to parameterize something that's the interaction between those two modes, which accounts for some stochasticity that can actually source some large-scale modes. So this can basically be parameterized in something like, so there is a UV physics here that we don't know, that basically this number that's here is telling you. And this comes very simply as the form of some derivative expansion. So you can find that this guy, the k to the fourth, you add here, basically accounts for a k square constant mode that basically interacts with another k square. Okay? So it's just some derivative expansion that's missing here for the whole stress energy tensor. So you're saying that basically there is some stochasticity in this guy that has an analytical form, which is k square. And this k square interacts with another k square. So this guy, basically this UV should enter as some derivative expansion. And when you have a k square multiplied with another k square, you can source basically something that's k to the fourth, which is something that adds directly to P choo-choo. So this is some derivative of some stochastic components. So there is some epsilon here, which is some stochasticity, which you don't know what exactly it is. Right, so there is some, what you're saying is that there is some intrinsic small scale physics here related to very small problems, like very small scale problems, which you don't know. So it's some expansion on top of some stochastic field that you don't know exactly what it is. Okay? But you know that it assumes some form of power law expansion in terms of derivatives. So this is what we have here, k to the fourth, and just to have the correct scale on this guy, we normally divide by k now to the fourth. Because then this guy becomes dimensionless, right? So what we are going to assume for sigma j, okay, so let me anticipate this. What we assume for sigma ij is that it has a form of something that depends on some COs times some operators, O's here. So as I said, we're not assuming any form for sigma j, but instead we are taking the most agnostic approach of parameterizing the general sigma j, sorry, this is sigma, as something general, as some counter terms times some operators. And those operators are the most general operators you can have that can be written as a function, let me write here, phi g of the gravitational potential. So this, the reason why you have this, it's a very generic thing, but the whole point here is that it's a very generic operator that depends on the observables you have in the problem, and the only things that can appear by GR, which are derivatives of sigma ij, of phi ij. Huh? Why not delta directly? Okay, if you try to do with delta directly, you're going to find there is something missing actually, because delta is basically the trace of this guy. Right, so it means you're missing some non-trace component, which are the Galilean operators. I'm going to talk about the Galileans later, okay? And also, there's something else here, which is phi v, which is the velocity potential. Because we have two different equations, one for the velocity and one for delta. So for delta, you have this equation. So you have something like phi g equals to delta, but as I said, delta 1 is equal to theta 1, but when you go beyond linear order, theta and delta are different fields. So those are two different degrees of freedom, which means you also have to have a different potential here, which is something we call phi v, which is basically a Poisson equation related to theta. And this basically tells you, okay, we have two different degrees of freedom, one for delta and one for theta, one that gives you the F kernels, and one that comes with G kernels. Okay? So it's just a generic way to write down theta, the whole theta field, in terms of another field, which is phi v, because you always have to have two derivatives to be physical, right? So it's just the field associated with theta in general. Because you have two different equations, one for the density and one for the velocity. And you can think about, you have two fields, so you have 2 degrees of freedom, which means you have delta and you have theta. Both are related to the same initial conditions, which are delta 1. But physically speaking, the evolution of those two fields are different. So because other equation is going to drive basically the velocity, also coupled with gravity. So gravity basically generates another. So it's basically the full evolved density field is here, and the full evolved velocity field is here.
That somehow can be imagined that if you go to the nonlinear regime, you can have the same kind of density distribution with different velocity. It's very artificial to include like this extra potential for the velocity.
So
Somehow it's arising from the fact that you are pushing this to scales in which you cannot account for here.
So it's not artificial in the sense that, so this is what's going to source basically gravity, right? So this is basically the gravity source. But there is an extra piece of information, which is the velocity field. So any observable, what I'm saying when I expand both in phi g and phi v, is that any observable you have, any single observable that you have, can only depend on the two guys that you have here in the equations, which are delta and theta. And you can come up with some potential for them, which are phi g and phi v. So they can only depend on basically the components of phi g and phi v with two derivatives. The trace is delta and theta, but generically they can depend on both. So it's just a way to redefine this field and come up with some extra generic potential. Definitely, there are off-diagonal components here as well.
But in the original equations only worry about theta. I don't see why you would have like, you now make this sort of potential that it's somehow accounting for the effect on theta, but I don't see why then you have extra degrees of freedom coming from off-diagonal components.
So for this, it's clear, right?
Yeah.
For this, it's clear. So the point is that gravity acts via this, so that's why we have this field here. But for the velocity, it means that there is, at every single point in the sky, there is basically an off-diagonal component as well. So this accounts also for what's here as well, right? So it's a bit tricky, it's a tricky argument, but the point is that it's a way to basically embrace the degrees of freedom inside theta without having to write down. Yeah, as well, definitely. Yeah, as well. Okay.
I just couldn't turn way back. So just to understand the common terms. So you have this huge field that we all understand, and you have two pieces. One that's divergent, and the other one related to the stochasticity of the field. The number that you have in front of your page before comes from the factor that you need to use to get away from the divergence.
So first, like, yeah, as Rogero mentioned, in the case of lambda CDM, there is no divergence here, but there is a lambda dependence. So what you're counting here for is for the lambda dependence.
So this is the number that you need to include to remove this dependence.
Yeah, makes sense.
Case before is the thing coming from the stochastic.
Yeah, which you don't know. So this can be understood as some generic epsilon term here, which has a constant part as well, so that doesn't go as k-square. But you know this k-square point, k-square cannot enter in the matter part. So just by the conservation of energy and momentum here, you can show that this epsilon for matter cannot have a basically k to the 0 part. So the first guy that enters here, for matter at least, has to be always k squared, which means that when you take cross correlations, it enters as k to the 4th. Okay? And this comes with the fact that you have a derivative here, extra derivatives here appearing. So this. Okay? So the P22 term is going to be regularized by something that goes as k to the 4th, but the P13 term is equal to P of k integral of F3 of P minus P k P of P, right? And this guy goes as P square, P of k square over P square. So when P is larger than k, okay? This is just a number times k square times pk, because this pk is outside here already. Just you have the correct dimensions, I'm going to divide by k now square. So it means that if I want to subtract something, so if I want to basically cancel out the UV dependence on P22, I have to take delta 2 to be equal to delta 2 of lambda plus some k square over k L square times a number. Okay? And for the P13, if I want to cancel out the dependence on lambda, I have to add something like, and this number here we call C stochastic. And this delta 3 here, if we want it to be lambda independent, it has to be something like delta 3 of lambda times CS square, or minus, let's put a minus here, because we're subtracting things. So k square over k and L square, delta 1 of lambda. Delta 1 here. Here's delta 1 and here's delta 3. So then you can ask, what exactly does it mean to add this CS square here and this C stochastic here? And it means to take this C here to be CS square and the O's here to be simply something like k square delta 1. The reason why I call it CS is because it has exactly the same phase, so CS of lambda, sorry. There's a lambda dependence here. So you can check that this k squared delta 1 that you add here has exactly the same phase as something that relates to a sound speed in a fluid. So it says has exactly the same characteristic of sound speed component. So that's the reason why we call it CS, because it basically parameterizes the first guy that can appear, which is a k squared delta 1, which basically accounts for small fluctuations on top of non-perturbed fluid. So this is exactly the same sound waves propagated in a normal fluid component. Exactly. Exactly.
Then somehow you're defining by these dependence some pressure.
Exactly.
Currently pressure.
So this is an effective pressure term that would appear that basically didn't appear in the perfect pressureless approximation. So this accounts as something as an effective pressure term that enters at leading order. You're right. Okay. So then, okay, so this was the one loop part. So those are the two loop results. And what you see for the two loop results, so you compare the tree level result, which is in green here. So what you see is that the tree level result basically fails. Oh, I have to remove this bar from the. Yeah. So the tree level fails around at person level already from the scratch, right? Before 0.1. But when you do the one loop calculation, you see that it fails around 0.3. While the two loop calculation, you can actually push towards, very small scales. Okay?
Why do you have the extra
In the tree level, this one here? Good question. I don't know what they did in this plot, but it should go to 1 on large scales. Maybe it's an artifact from being in linear scale here, not in log. Oh, so dash means SPT without adding the counter terms. So when you don't add the counter terms, you see that the one loop fails here, already here in this part. But when you add the counter terms, the one loop basically is fixed, right? So the one loop fails, sorry, the one loop is this one, so it fails here in this part. But when you add the counter terms, it's fixed up to k.3, around 0.3. For the two loop, it fails already more or less in the same scale when you don't add the counter terms, but after adding the counter terms, you basically can correct it.
the oscillations are coming from the integration?
Good point. So what are those oscillations? Why do we see those oscillations? So when you see this plot, you say, okay, I don't trust the EFT of LSS result up to % level because I still have those oscillations here. So on top of doing this whole story, you have to do something called IR resummation. So the wiggles you see here are basically artifacts because you are in the Eulerian picture. So when you are in the Eulerian picture, you're basically not accounting for large displacements in the fluid. So basically, you have to subtract these displacements you have in the Eulerian picture because it's something that people pointed out many years ago. But it's just the fact that when you're in the Eulerian picture, you're not actually taking into account what happens on the large-scale displacements, so that the particles can travel through large scales and basically move, for instance, the BO and things like this. So this is an artifact. The wiggles you see are an artifact of the frame you are. And you can actually resum these components. So there's a part of this component you can resum to get rid of those wiggles and restore and have % precision. If I have time, I'm going to talk about this later today. But I think it's just the error bars. I think it's just the numerical error bars they get. I think. I'm not sure. So the counter terms here are fixed exactly in the simulations they have to reproduce the correct simulation. So it comes with a price of having some terms, of having some free parameters, but those physical parameters are physical, and they correspond exactly to operators, the most generic operators you can construct here. So each one of the C's here have a physical meaning which is associated to the operators they have. Okay? Yeah. Yeah, so this is what happens actually here in the blue one. It comes with some extra parameters. And something actually we have a point out when you go to tree loops is that the fact that tree loop reproduces the correct result doesn't mean it's not overfitting. So being physical, I mean, just by the power spectrum has a very simple shape. So it's something that goes up, has some wiggles, and goes down, right? So the fact that you have many free parameters actually allows you, of course, to fit this function pretty well. The fact that you can fit this function pretty well doesn't mean you're getting the correct prescription for this. You can be overfitting, as you said. So the scale cut you have for the true loop, the fact that you can reach those scales here, doesn't mean that you actually have the correct prescription. So you have to consistently go either to higher endpoint functions, so the bispectrum or the trispectrum, or to go to higher loops as we did for the tree loop to see actually that something here happens that actually the tree loop is basically overfitting. That tells you the tree loop is overfitting. Right, so this is everything I had to say about the matter part. So let's move to the bias part. So as I mentioned, yeah, we did tree loop. So what happens at tree loop? I was planning to talk about that later. But okay. We did. But, okay, but for the matter, yeah, I'm just gonna go through everything and then I go slowly again through some of those points like IR summation, Redshift-Space Distortions, and other things. So. Yeah, let me briefly finish this bias component part. So as I mentioned, so the whole prescription we have derived here is for matter. And for matter, we have the equations of motion for matter that help us a lot. But as I said, what we observe is something like the galaxy density field. So we have to connect delta G with delta. So how to connect those two things? So for the one loop, it's one. One counter term, which is the CS square that was there. For two loops, it's 4. For 3 loops, we had something like 11 or 12. Yeah, you just have to add more and more operators here. Higher dimensionality because you're also going to higher dimensionalities in delta 1 when you go to higher loops, which means you can go to higher dimensionalities here. Yeah, but here you see, okay, there is a double power counting here, right? So there is a power counting in K. So when you go to the one loop, here you have, okay, 4, right? Here it's 4. And here it's basically 4 as well, right? But this guy is actually next to leading order. So you can show that, so the counter term for the counter term, let's take P13. So for the P13, we have something that's P, case for the leading party, it's basically order 4 here, but you have order 2 here, plus a K square. So this is order 4. But it's true, like if you count the stochastic, then it's 2 free terms. But the stochastic part you would have anyway. I mean, this stochastic part you have to add, I mean, this is the usual shot noise part, it's just some scale-dependent shot noise, right? I'm not counting this as an extra counter term because this enters also in the shot noise, you know. It's not something that comes as a counter term per se. It's what do you mean? Yeah. You mentioned you're talking about the Galilean part, or? Yeah, you have delta square here as well. So at one loop you have delta 1, but if you go to 2 loops, you're gonna have something like delta square. So this guy comes from a delta, right? So what you're saying here is that delta, let's say, lambda independent is basically delta, lambda dependent, plus some delta k square delta, right? But you also have something like a k square delta square. This guy is here as well, but it is going to enter at higher loops. So this is lambda dependent, right? But it's going to enter at higher loops because it has a square, so when you do the power counting, you can check the enters at higher loops. But you're right. When you go to 2 loops, this guy has to be there. And also higher powers as well. And also something like k square G2, which is the Galilean. I'm going to talk about the Galilean now.
Sorry, one more question. So, I'm sure you mentioned, but what is the operator that goes in front of CS squared?
Of CS square, it's delta.
No, but in terms of in the sigma ij,
In the sigma ij here,
yeah, there's some, so one of the COs is CS, right?
yeah, so one of the COs is CS. What you have here is a delta, which means di is a k. You gain a k, you gain an extra k here.
Then an extra K.
And the other k comes from the derivative of v.
So the operator is delta?
So the operator is delta here, because then you have a derivative here, which is k.
But it said that it has to be phi,
Yeah, you're right. So it has to be delta I, delta j of phi. But then you contract with a delta, with a Kronecker delta of ij, and you gain delta. Yeah. Yeah, 2 derivatives actually.
Then you mentioned something in the very beginning about symmetries. How do you know that this does not violate different constant invariant?
Ah, you can show this. You can show. Yeah. No, you can, but you can show that this is what you need to be boost invariant. So this is what you need to be boost invariant. I mean, many people have shown this. That those building blocks you have, delta I and delta J, are the components you need to be boost invariant.
So not breaking the principle.
No, by having delta I and delta J, no. You always have to have 2 derivatives. With respect to EDS metric? That when you go from X, that delta X. Yeah, you can show that this is what preserves, because this is what preserves the equivalence principle. So 2 derivatives of phi is what preserves the equivalence principle. And that's what you have to have the full GR set of symmetries.
So the operators can be only powers of the J.
Yeah, they can only be contractions of this guy. Right, so for the bias, the question is, again, writing down the most generic expansion you can have. So you think about the most generic functional you can construct on top. You can ask again, what's the most generic functional you can build? And historically, what people consider for many years is just to have a linear relation between delta G and delta. So you just assume that delta and delta G are related linearly via a coefficient B delta. And the intuition why to assume this linear relation here is actually quite simple. Because if you take P GG and divide by P MM and take the limit in which K goes to 0, this has to go to some constant, right? And you call this constant the bias. So you see, you don't have to talk about any loops. Everything here is tree level. So this is tree level, this is tree level when K goes to 0. All the loops cancel out when K goes to 0. So to define B delta, so this is a first order bias. We can use the 2-point function on large scales. The problem is, if you take this relation, and if you go to K, as you increase K, The problem is that it fails. If you just try to compare two simulations, you're going to find that you cannot fit a constant when increased k. So there's something that people for a long time called scale-dependent bias. Which is basically trying to correct this or to promote this B of delta, just that you have some k dependence. But here we're not going to try to do something like this, but instead we're going to ask what are the other kind of operators you can add to preserve the symmetries that, as I said, boils down to include basically derivatives of phi g and phi v that allow you to write down a most generic expression for f here. So I'm going to promote this, and so the next guess people had here, like, okay, first people tried this, and then the next thing they try is to promote this to also include something like so this is also motivated by peak theory, and this comes with the name of linear in matter density, or linked approximation, plus some extra powers of delta. So you can put delta cubic here and other things. Okay. Yeah, local matter. Did I say linear? Okay, local, sorry. It's not linear in the matter density, of course. Right, it's also motivated by peak theory. So this is just an attempt to generalize this expression to also go to nonlinear scales, such that you improve what you would see in simulations, for instance. But as we see here, and something you can see is that this is basically the trace part of delta. So if you just contract this delta I, delta j with a Kronecker delta, you get something like delta. But okay, but when you go to higher orders and you take this square, you have an extra component, which is not only the trace, which gives you the trace square that gives you delta square, but you also have some extra component, which is the off-diagonal component, which is phi. So this is the degree of freedom that's missing here in this expression. And you can show that this is actually necessary, as I'm going to show you now, if I have time. So how much time do I have? 40 minutes? No, 20 minutes, right? 30 minutes. Yeah. Okay, so I'm going to rush.
No. You can continue. I have a doctor's appointment.
Okay, so.
No, you go ahead. Carol will take over.
So there are many ways you can see there's something missing here, and people realize for two different reasons. First, they realize it's not a good fit, and they realize actually this component, there is a dependence. The scale dependence can be fixed by adding this off-diagonal component here. So this is something that historically people notice. But there is also a very beautiful intuition why you have to add this off-diagonal component. And the intuition comes via normalization. So if you try to compute loops and to add all those operators, like for instance delta square, delta cubic, you're going to find that there is something missing. Because as you move from one cutoff lambda to a different cutoff lambda prime, you're going to find that other operators are going to be sourced. Which means if you have a basis that's complete in one cutoff lambda and you smoothly move to another cutoff lambda prime, the basis is not complete anymore, just because there is something missing. So let's generically write down something. Delta G is equal to B delta plus B delta square. So let's suppose this is the expansion we have. So it means that we have a sum of B O's of delta here, in which O's are equal to delta and delta square. So the problem now is that if you take these bases, there are the following questions we can try to address. Is this basis complete? The second question is, what's the most general? And the third question is it UV sensitive? Because as you include this term here, this delta square here, delta square of k in Fourier space, it's just equal to this expression. It's just a convolution again. And when you try to analyze what it means that if I take two modes, P1 and P2, which are deep in the UV, so large modes, they can actually source a K mode. So this is what this Dirac function here ensures. So it means that either I trust my delta prescription here to very small scale, so it means very large piece, or something is going to happen here, and I'm going to have to smooth these fields. So I'm going to have something like that's lambda dependent here again. Because if I don't write the lambdas here, it means I trust my deltas. If I know the prescriptions for delta down to very small scales. Because those two deltas of P1 and P2 can sum and lead to a K that's actually short and within the perturbative range. Make sense? So it means that naturally when I write something down that's a delta square here, I have to add these lambdas here. I have to do it. So this is what we call composite operators. In the context of particle physics, we call it composite operators because they're the square of the same field in the same point. So this is a delta square of x. And whenever I have delta square of x in the same point, it means that I have either I smooth it or I'm going to have to trust my prescription down to very small scales. And the reason is exactly this one. They're very UV sensitive. Okay? So the answer here is yes, it is UV sensitive. And you have to regularize this. You have to add something. If you either you promote this to depend on lambda and this to depend on lambda, or you basically remove the lambda dependence here and add something that's a counter term that depends on lambda. That cancels out the lambda dependence here. Okay? Well, you can define these counter terms to be another operator. I mean, I'm writing something very generic here. But I want my B, so I have two options. Either I promote those B's to depend on lambda, or I add some counter terms here to the operators that cancel out and keep my B invariant. Okay? So the generic way to write it down is the following. Or I have two options. Either I promote my B's to be lambda dependent, and I keep my operators lambda dependent. Or if I want my B operators to be lambda insensitive, I'm going to define these B parameters that are lambda insensitive to be renormalized with an R label here. And I define something which is a renormalized operator O with those two brackets. Okay? So I'm going to explain now what I mean by this. And the way those B depend on lambda is something I'm going to talk about tomorrow. And this, understanding exactly how those B depend on lambda, is exactly what happens as you zoom in or out in your theory. So this is what we call the galaxy bias renormalization group, or the large-scale structure renormalization group. Understanding the dependence of each one of those parameters with lambda, with the scale, with the smoothing scale of the problem, and promoting those B's to depend on lambda is something that we want to explore. But for now, let's focus on something, let's try to understand the lambda dependence of those operators.
The same thing should happen in the other expansions.
No, it's the same, it's the same. For matter, it's the same.
Should also depend on lambda.
Right. So Rogero has a point. So it was there before, right? CS depends on lambda, and we have to understand how CS depends on lambda. The cool thing about this is that I can always take B delta equals to 1 and BO equals to 0. And then the whole story here is just the matter expansion, right? So the bias expansion is exactly the same thing we had before with one specific set of bias parameters we choose. So this is something more general. All included, everything here, everything in the bias expansion. When we talk about the matter part, the only difference is that we have the equations of motion that fix you the G and the F kernels, and fix some part of the counter terms as well, because you cannot have all the counter terms. You cannot have k to the 0, because you have the equations of motion that fix some extra symmetries for the problem. But here, for the bias expansion, we're thinking about something more generic, which of course embraces the whole matter story. It's just one specific case of this whole bias expansion. Clear? Yeah.
And I'm sure that that would affect the galaxy population that you have there. But in here, in principle, you are only having the dependence on position and dropping the formation history. I'm saying that somehow I don't see how these can capture something like assembly bias. That I would be sure that it would somehow capture.
So assembly bias, so what you're writing down here is basically the assembly bias enters when you try to specify what's the tracer population you have with some features, right? You're trying to add some features and think about how to split the bias part. So here is the most generic operators that can appear. If you try to split and think about some generic features, like for instance, I don't know, what people think for the assembly bias. So the same matter field, delta can be the same for two different delta G's. Yeah, that's true. But then the bias operators are going to have to be different, right? So to be clear, each one of the operators you write down in the bias expansion, like the O's you assume here, have to be orthogonal to each other. So the fact that they are orthogonal to each other means that there is only one set of those bias parameters that describe this galaxy density field. Make sense?
So the operators that generate the galaxy population of luminous red galaxies different from the operators that generate the quasars.
The operators are the same, but the bias parameters that come in front of them are different. The operators are just products of these building blocks here. Yeah, yeah. Always the same operators you have. Okay? Okay, thanks. Right, so what I'm going to try to describe now is what I call this guy, how to define this guy. What's this object here, which is the renormalized operator? How to define something that's lambda independent here? Because as we saw, if you add lambda, if you add delta square, this guy is going to intrinsically be lambda dependent. So you have to add something else that makes this object here lambda independent. So this is what we are searching for. So this is lambda independent, this is lambda dependent, this is lambda dependent. The question again is, what's this? Okay?
So these renormalized operators, you can always only renormalize at the level of the power spectrum, right? So like you have to be trying to answer.
No. No. So this is something you can think about them. So there is always one prescription to define this guy. There is one arbitrariness choice here, which is what's called renormalization scheme. Sorry. That's arbitrary that you can choose. And the way we're going to choose this is via the power spectrum, or the bispectrum, or endpoint functions. You're right. But this is not the only way to define how those operators live. So you can do it at field level as well. So the way to define this renormalized operator, you're right, we're going to use the endpoint functions. But you can always think about O's like at field level themselves. O's as, because at field level, they're always going to depend on lambda. So this is, well, things mix with each other. That's, you can define this at field level, but the way you define this condition is going to be, so this is a field level statement, right? But the way you define this renormalization scheme is going to be via endpoint functions. You can define this via multiple ways. The way we're going to fix the scheme here is using endpoint functions. Yeah. You're right. For the bispectrum, it comes with new terms, which means you have to fix extra conditions here. I'm going to explain what I mean by this now. So let me explain what I mean by this. So here we see a very specific way to define the linear bias. And I never had to mention loops or lambdas to calculate this guy, right? So this is a tree-level statement. PGG is a tree-level. So when you take k, like it of course has loops. But as I take k and bring to 0, and same for PMM, as I take k and bring to 0, this is a tree-level component. So no loops here involved. Here is basically, what you're doing is to use the second point function to define the linear bias. Then the question is, we saw that delta square depends on lambda. How can we take the B delta square, the guy that comes in front of this, and to define this to be lambda independent? Because this is going to be the renormalized delta square. So the question is, what about B delta square? Because this is the renormalized delta, right? Can I do something similar for B delta square? Can I come up with something that's a tree-level expression that defines the renormalized delta square? And we know there is something we can do, because if I take an operator, I'm going to explain this notation in a minute, but this is delta square. It's just a convolution. So this is K, so this is P, and this is K minus P. Exactly as I wrote there, right? I can take this operator here, and I can contract with something that's like this. And then it's a tree-level diagram. So this delta square here, the way you define this, if you take contractions with two linear legs, it doesn't depend on lambda. So this is a tree-level diagram. So all that to say that I can take my B delta square as a limit of the bispectrum of B, let's say 211 galaxy matter divided by B 211 matter. When K, sum of the K configurations, because you have different K configurations, K1, K2, K3. You can take the K's going to 0 and define this B delta square. So this is a tricky question because you can take combinations of those K's, but you also have combinations of those K's, but you also have B, G2, which is this other second order operator you have. So each one of those here is going to be a different combination of K's that you bring to 0. But you can show you can do it. But it's basically the limit of the 3-point function. So here we take the 2-point function, the ratio of 2-point functions, to define a first order bias. And here we take the ratio of 3-point functions to define the second order bias. All to say that there is always a 3-level diagram that defines an operator without being lambda dependent when you take K going to 0. If you want to go to the 10th order operator, you can use the 11th order endpoint functions to define the 3-level contribution to this operator. The delta here, you have, but you already fixed this one with the 2-point function.
No, nabla.
Oh, but the nabla is when you take K and go to 0, K going to 0, the nablas go to 0 as well, right? Nabla is K square.
So what I'm saying is that, okay, you increase term by term these, and I guess that you can go to higher and higher endpoint function.
Yeah.
Is that sufficient to have the full, like determining the different bias parameters that enter at a certain order, or do you need something extra?
I'm not sure what you mean.
So we did, you do the limit from when K goes into 0 plus the power, the ratio of the power spectrum, and that gets you the delta.
Yeah.
You do it with the bias spectrum, and that gives you the delta square.
Yeah.
So forth.
Yeah.
Is that sufficient for the whole galaxy bias expansion?
Yeah, it is. So this is what I'm doing here is to define this guy with a 3-level contribution. So it's just a way to define this guy in the large scale limit. So you can always call what you call renormalized bias the limit of some endpoint functions when they go to 0. Some specific combinations of K's going to 0 give you the bias parameters. So this is the same in particle physics. When we think about the electron mass or the electron charge, we learn like in QFT lectures that those depend on the scale you are, right? Like this is what we call like the renormalization group. That if you do a measurement on 2 different scales, those constants will give you different values. They are not constant actually. So this is the same, but when we think about intuitively, the intuition we have about the charge and the mass are basically the IR limits, like something you do like in a lab like this, like here, right? We always think about the IR limit, which is K going to 0, to define something like it's a way to define, to fix those conditions. And the freedom you have to choose this basically tells you where exactly you're putting the counter terms. What exactly are the counter terms absorbing? From which to which scale? Where? So it basically tells you each one of those CS of lambda, are they contributing, like, are they basically absorbing which part of the loops? So you always have to choose to absorb. You always have the freedom to choose which part of the loops those CS square can absorb. Okay?
So this, because it seems like a bit of a magic. Suppose that you compute up to the 3rd term, and the way in which you would do it operational is you just measure from the galaxy the 2-point, the 3-point, the 4-point.
Yeah.
You have the ratio, and now that you have those parameters of your galaxy bias expansion, let's say that now you compute the power spectrum for the galaxy.
Yeah.
That will allow you to go to smaller and smaller scales and capture.
Actually not, because this is just the lambda dependent part, right? You still have, like, as I said, the counter terms absorb two different parts. One is the UV part, the other one is the lambda dependent part. So here we are just fixing the lambda dependent part. There's no magic. I mean, I'm not gaining. I'm just using one choice that I have, which is the choice to say, to define what I call lambda dependent. Okay? Clear?
You lost me with the diagram.
Okay.
What did you do there?
Okay, so the power spectrum is always something like this, no? K1 and K2, right? And what I had here before is something like this, which is the F kernels, which I connect, right? I mean, generically, I can connect them here, okay?
That case, you're doing for the P delta, you're doing a tree level, so it's just a straight line.
Exactly, so here is just delta N, and here is just delta N. There is no higher, like, there is no bias expansion. There is no other operator more than delta. So this is just delta, delta and delta. Delta to some order N. So this is delta, and this is delta, right? Now I have two different things. I have first a convolution that tells me what's the operator I have here. So this is the convolution of delta square. And then each one of those legs, I can expand as some F kernels. So I can take each one of those delta here and expand as some, which has an extra convolution. Okay? Make sense? And then I'm just taking the linear here. So this is delta square, and contracting with something linear. I'm taking the linear here. So this is delta 1, and this is delta 1. Almost over. Okay, let me just finish this part. I need 10 extra minutes. Is this fine? No, peak hours in January. No, it's fine. It took me 20 minutes to come from my place to here today.
Someone is going to say, oh yes, peak hours. I'm going to stay here half an hour more.
Exactly. I see you at. I stay here at 8. Oh, I shouldn't have erased this. Okay, let me erase this part. Right, so mathematically, how can I write down this expression here? This expression, what's the most generic way to write down this expression? And so if I write down this expression here, what I'm doing in this diagram here is to contract each operator that I have with n external legs, right? So I have an operator that depends on lambda. So this depends on lambda. And I take contractions of this operator in a point P with n external legs. So this is what I'm doing in this diagram, right? And this part I can split in two different components. One, which is a tree-level component, which is the one I wrote down. there's, of course, loop components to this part. So I can just come here and compute, for instance, loops. Right? So whenever I take the cross correlation of an operator with other external legs, linear legs, I can expand this operator in higher orders here and take 3-level contributions plus loops. And of course, as I said, my operator also comes with some extra counter terms. So I also have something which is the cross correlation. If I take this plus this, it's going to be something like counter terms, which I'm going to call generically CT of lambda. Okay? Yeah. Yeah, exactly. Exactly. I gain extra factor. So this is suppressed compared to this, right?
Why?
Because it's a loop contribution, and this is a 3-level contribution.
In that case, that's going to be exactly the renormalization term, right?
So what I want is this lambda part to cancel out exactly this part. This is exactly what I want. So I want this two contributions to sum to 0. Such that this guy here at 3-level is exactly equal to my renormalized operator. Okay? So if I just take this, I'm just substituting this part here inside this and opening the first part into 3-level and loop contributions. So what I want to enforce is this relation here. So I want my counter terms, the part that's lambda dependent to exactly cancel out the lambda dependent part here of this term. Okay? Right, so oh, my battery is running off. Okay, I'm almost done. Huh? I think this computer is here. Yeah, they're seeing my screen. I think they're seeing the video, yeah. So I want to enforce this. I want my loops, my counter terms to cancel out exactly my loop contributions. So you can, I leave this as a homework, but you can show that in order to enforce this, so you can exactly define this renormalized, for instance. Let's do for delta square. For delta square, we have those kind of loops, so we can take contractions first with 0 external legs. So take n here and take to 0. So for delta square, it just means that the first loop you get is something like this. So this is n equals 0. N equals 1 basically give you something like this. And n equals 2 give you something like this. So there are two diagrams at n equals 2. And when you compute those loop diagrams here, basically you're computing those contributions here, basically to find what are the counter terms you have to add. So you find that the renormalized delta square, this is something you can compute, is equal to delta square of lambda minus sigma square of lambda 1. The 1 comes from this diagram here that doesn't depend on any other operator, plus 68/21, which is a magic number, delta of lambda, plus 8126/2205 delta square of lambda. 8126/2205, magic numbers. This is very important to copy. So what you see here is that the 1 comes from this blob, so it means that to renormalize delta square, you have to subtract the variance of the field at first order, and then n equals 1 tells you that you have to subtract something that goes as delta, which is what you see here. And you also have to subtract something that goes as delta square. But something that's nice is that there is an extra term here. So in principle, if it was just this, everything would be fine, because it means to renormalize something like delta square, sorry, there's a square here, you have to add something like delta and delta square, which means that the basis would be complete, right? It means that everything would work fine here. But you actually find something else, which is the fact that you have to add something like 254, 2205 G2, in which G2 is equal exactly to the off-diagonal part of phi G. So there is a new guy that if you want your basis to be complete and the renormalization that you have to add. So this basis here is not enough, and you have to extend this basis to include at second order also a G2 operator. Which means it's not enough to include the trace of delta ij. And similarly, you can check that for the velocity if you go to next to leading order. That's not enough to include the trace of the velocity. If you want the basis to be complete, you also have to include the off-diagonal part of the trace of the velocity. That's one of the reasons why it's not enough to include theta here. You also have to include other things. If you want to be complete under renormalization and to have all the degrees of freedom to cancel out all the possible lambda dependence, you have to go beyond. Here you see for phi g, but if you go to next leading order, it's going to also appear for the velocity. And this comes like the fact that you have to include those is basically just a natural consequence of GR, of the symmetries of the problem. This is, I mean, you could have as an ansatz that this is what you had to include before, because those are the most generic operators that GR enforces you to include. Okay? So these ones here? This one here? No. So this one, no, it's delta 1 and delta 1. I'm just computing these guys here. So this guy, if you want this, so this is this part here, right? And what you have to add here, so you would have to add something like, and a G2 here as well, sorry. To basically cancel out the lambda dependence of this term. Okay?
So basically, you So you get delta T, this is the most spectrum diagram, so stop right there. There's a neon, but naive. But then you compute the contribution, you see that when you do that, you still have a lambda dependent, and then you realize that you need to add that extra
Exactly.
diagram, which is not encompassing this delta 1 loop contribution.
Exactly. So if you want your basis, if you move, I'll just say that if you take one lambda, do the calculation including delta square and delta. Take this basis here. Compute everything at this lambda. And then, for some reason, like this lambda is not physical, right? So I can take another lambda prime. Then you're going to check that the basis you had here for this fixed lambda was not enough. That this basis, there is something missing in this basis, and there's something else that has to be included for this basis to be basically, to contain all degrees of freedom of the problem.
How do you read this in terms of the delta 1 and 2 load? I'm lost in this.
How do you write what?
Because here you're doing everything in terms of the, when you're enforcing the condition that you captured to cancel the loop contributions, you're using the linear.
Yeah, yeah.
How do you know that that's the case? The unique, I mean, this T2, how does it appear in that particular line that you wrote up?
So how did it appear here? Because you can check that when you calculate those loops, you're going to see that, I mean, you can plug in Mathematica and ask Mathematica to solve, and you're going to find that there is something that's this part here, especially this part here, delta I, delta J phi, is going to be a reminder of this calculation that cannot be canceled. This part cannot be captured by a delta square. So when you do these loop computations here, so what you're saying is that, like, suppose I take my operator and I trust this. I have tree-level contributions and I have loop contributions. But I want my thing to be lambda independent. But when I do these loop computations here, I see that the O's that I had before do not form a complete basis. Because there are some of those contractions here that are going to display some off-diagonal component. So this is the line of thought. Take the basis you had, do the calculation, you're going to see it's not enough. You're going to have to add something else to this basis. And this something else you have to add tells you that, okay, now I added G2. And then I can do the same. Take my G2 here and plug my G2 instead of delta square, do the renormalization of G2. You can do the same, the renormalization of G2. And you can see that the renormalization of G2 contains basically G2, delta square, and delta. It just means that this set of operators here, when you move from lambda to another lambda prime, they're basically rotating internally. And if you just remove one of them, you cannot rotate again when you go from lambda to lambda prime. Okay?
And then if you add an extra leg to get the third order, then you know that you need this contribution, but the contribution stays at this size, you're going to see that there is a piece missing from the gamma theory.
Yeah, because then if you go to next to leading order here, you're going to have some extra pieces that are not only delta, delta square, you're going to have delta cubic, and the third order operators. Okay? Yeah, I think it's over. Questions? We go to a bar and you can ask me.